So this is the Unit 7, Day 2 lesson, and we're on video number 2. We're going to look through an example here where we're finding the local max and min of a periodic function. So we have a trig function here, f at x equals sine of x squared. A little bit different than anything you've probably graphed before, because until now, until you knew derivatives and calculus, this is not something you could graph just with regular transformations of trig functions. So we're going to first take a look at finding the intervals of increase and decrease of this function. So we need to find the first derivative. So f prime at x, we take the derivative of the outside function. Derivative of sine is cos. So I have cos of x squared, then times the derivative of the inside function, which is 2x. So simplifying this a little bit, we have 2x cos x squared. I always like to pull out any multiplier after a trig function just so that it's really clear. Pull it out front so that it's really clear that that's not part of the angle. It's just 2x multiplied by that cosine function. So if we're looking here for our critical numbers, we need to consider both cases where f prime at x equals 0 and f prime at x does not exist. And again, even if this is a little repetitive or a little obvious that there aren't any restrictions where it doesn't exist, I still want you to write that out so that I see that you've at least considered both cases. So here, there are no restrictions. Cos, it has no restrictions on the domain. 2x has no restrictions on the domain. So there aren't any cases where the first derivative does not exist here. Where this derivative equals 0, though, so we have to consider, first of all, obviously when x equals 0, that would be a 0. And also when cos of x squared equals 0, we would get values that would make the whole derivative equal to 0. So sometimes people, when we have a trig function with kind of a bigger, messier thing in the angle, prefer to do a substitution. So if it helps you, you can say let theta equals x squared. If you don't need to do that yourself, that's fine if you just kind of continue from here. So I could say cos theta equals 0, and then what would be the values of theta? Thinking about where the zeros happen on a cosine function, we would have pi over 2, 3 pi over 2, 5 pi over 2, and so on. So it would be pi over 2 plus k pi, where k can be any integer, if you wanted to write that as kind of a general sum there. Now that's just theta, that's not our actual x value. I'm gonna have to squeeze in, actually I'll move over here to figure out what x is. So if x squared is pi over 2, x would be the square root of pi over 2, or the square root of 3 pi over 2, and so on. And on the next slide, we're going to be graphing this from 0 to 2 pi. So I'm just going to kind of get sort of approximate values here. So this is about 1.25. Square root of 3 pi over 2 is about 2.17. If x was the square root of 5 pi over 2, that would be approximately 2.25 0.80. So you can see that these are actually getting closer together, and some interesting stuff is going to happen with this graph. I'm just going to keep going here. 7 pi over 2. I'm going to go until we get kind of a pattern in here. We can get a few different values and then we'll test it in the chart. I think this will be the last one. So square root of 7 pi over 2, about 3.32. So we can see that the values here are getting closer and closer together, and that will kind of show up in our function. That the x value here would actually going to be looking at, we'll set up a table and look at the critical numbers 0 and then all of these ones. Of course, without any end bound on this, we're going to have a really long table, but we won't kind of keep going for forever. So pi over 2, and then root pi over 2, root 3 pi over 2. We'll maybe just do a couple examples here, a couple steps of this table. And then root 3 pi over 2 and root 5 pi over 2. It will kind of continue in a pattern. So I'll just do the first few. And we can look at the value of this function. And this is maybe actually a good candidate for doing just test values. So if we subbed in to the derivative, square root of pi over 2 is 1.25. So if we substituted in f at 1, say for instance, so in my table, I'll put test value, I'll just put a 1. And then I want to say what's happening to f prime and what does that mean about f. So maybe 1.5 in this next, I guess I could have done a 2. And then 2.5. So you can substitute in these values and into the derivative and just see, is it positive or is it negative? So if I'm substituting in 2 times 1, obviously going to be positive. And the cosine of 1 is positive. So this is going to give us a positive value and mean that our function is increasing. If I did cos of 1.5 squared, all of a sudden I get a negative, so our function is decreasing. So we're going to see a periodic situation here, and you can kind of pattern it out as far as you need to figure out what the pattern is and how this is happening. So this is going to be a positive and increasing. If I picked another number, say a value of 3 for the next interval, you would get a decreasing. So it's increasing, decreasing, increasing. I'll squeeze 1 in, and then decreasing again. So another important thing to note, whenever we're doing calculus, of course, your calculator has to be in radians. No measuring in degrees at all for the calculus part of the course. So just if you're not getting the right signs on your test values, that could be why. So this can tell us that it's increasing from 0 to root pi over 2, from root 3 pi over 2 to root 5 pi over 2, and we would be able to kind of see a pattern there with these square root functions of where it's increasing and decreasing. We would be able to get these maximum and minimum points as well. So there's going to be a max here, a minimum here, a maximum here. So each of these values, not these ones because we would have to do the square root, so there's going to be a maximum at this one, a minimum at this one, and it's going to keep going in that pattern. A maximum here, a minimum here. So you would be able to pattern it out, adding on pi each time and keeping that square root sign, and you'd be able to get a pretty good picture of that graph. So what does this look like? we can talk about the intervals of increase and decrease. We can talk about the actual values. So we know we have a local max at x equals square root of pi over 2, square root of 5 pi over 2, and local min. To actually graph these, you would need to put these values in a calculator and estimate. We're not going to be able to get a really accurate graph because those aren't regular multiples of pi once that square root kind of comes into the picture. So then a local min would be at square root 3 pi over 2, square root of 7 pi over 2, and so on. So we would have our local maximums and local minimums. Okay. I have a graph from Desmos, which I think is kind of interesting to analyze. We could sub in these values into the original function, but actually what you're going to get, kind of hopefully unsurprisingly, this in itself really is just a sine function. It doesn't have any multiplier. It doesn't have any plus or minus. So the whole outside function is just a sine function. And we know that the highest value that sine of anything can take is 1. And the lowest value sine of anything can take is -1. So that's actually where these local max and local mins will happen. For all of these, y is going to equal 1. And for all of these, y is going to equal -1, which you can see if you start substituting those in. What's actually really kind of more interesting on this one is that if you look at what happens, that these max and mins, unlike with a kind of typical trig function where the maximum and minimum values are equally spaced, these are absolutely not equally spaced. You can see that it's almost 1 going from the first max to the next min, and then it's like about 0.6, and then it's like 0.5, so they're getting closer and closer together. And the reason for that is that squared, because we kind of have a multiplier in there, and the multiplier is increasing. So you can put this in on Desmos and look at it yourself. We do have the same axis of the curve. We have a maximum at 1 and a minimum at -1, but you can see that it's not actually a kind of regular periodic function, because a periodic function means that you'd be able to shift it over and it would exactly line up. These waves are getting squeezed closer and closer together. As you get into bigger x values, that x squared increases, not in a linear form. If you had something like sine of 3x, we know that that's increasing by kind of the same amount each time x increases. That value is increasing by 3 times it. But the angle in our sine function is increasing quadratically because it's an x squared, so it's going to go faster and faster. The other thing that you may notice is that this function is reflected. It doesn't go down from here. It's reflected directly in the y-axis. So here we see that whatever the value of positive, if x is a positive value here, it has the exact same y value for -x. So this is an even function in that f at x equals f at -x, which of course the only x value in our function is an x squared. So whether the number is positive or negative, when you square it, it's going to be the same thing. And just to kind of note that the frequency of these waves is increasing as x gets bigger, which we saw. Last example is probably easier than that one. Here we're going to look for critical numbers and just do a little test. Now, f at x equals x to the 1/3. This is not a real hard derivative. F prime at x is 1/3 x to the -2/3, or 1/3 times the cubed root of x squared. So if we've got kind of rewrite that a little bit. If we want to look for my critical numbers, so where does f prime at x equal 0, and where does f prime at x doesn't exist? So those are, remember, the two cases. You always write them out when you're finding the critical numbers. Here, if the derivative equals 0, are there any x values that would make that derivative equal to 0? No, there's not. The numerator is just 1, so there's no values. And we've seen lots of cases where there were values kind of on this side, but there weren't any restrictions. It can happen the other way here. Now, what value of x would make this derivative not exist? That would be a restriction, would be as if x equaled 0. So that's going to be my critical number. Now, if you look back in the original function, oftentimes the critical numbers where the derivative doesn't exist, the original function doesn't exist either, but that x equals 0 is just fine in the original function. That's going to be just the value 0, 0. So I'm going to take this, and it's a nice small table here. We only have 2 intervals. I'm going to create a table looking at this function, or the derivative, pardon me, from negative infinity to 0 and from 0 to infinity. I don't think that this is going to be too hard to figure out. If we have a negative value, as you can see here in the derivative, we've got an x squared. So if x is negative and we square it, we still have a positive number. Cubed root of a positive is positive. Multiplied by a third, still positive. So this is a positive value. That means that f at x is increasing on that interval. And if x is positive, obviously if we substitute in a positive number here, square it, still positive, take the cubed root, still positive, multiply by 3, still positive. The derivative in this case is also going to be positive, so it's increasing. So this function is a little bit of a funny one, that we've got this critical number, but it's not a local max or min. Remember that the increasing or decreasing, or the sign of the derivative, had to change for this to be a maximum or minimum value. So all local max and mins are critical numbers, but not all critical numbers are local max and mins. So here, what's the significance with this with respect to the derivative? So the derivative does not exist at this point. There is an actual value of the function at that point. So I could graph that point 0, 0 is absolutely in the domain of this function, but the derivative fails to exist. And what actually happens here is that we get a derivative that gets infinitely steep. So this function looks something like this. It is increasing for its entire domain, and at this one point the derivative fails to exist because it gets infinitely steep. And I'm going to kind of try and put a pen along here. So the derivative is positive, positive, getting bigger positive, and then goes vertical for just that instant, and then is positive again. So this is a continuous function. There's no gaps in the function. It is defined, but at this point it has a vertical tangent, which means the derivative does not exist. It doesn't necessarily mean that it's a turning point. You absolutely can just have some kind of inflection point at that area where the derivative doesn't exist, but the function still does, and it doesn't change from increasing to decreasing or vice versa.